Imagine running a massive 100 billion parameter AI model right on your laptop's CPU, hitting human reading speeds without melting your battery. Today, that sci-fi dream becomes reality. Welcome to our podcast, Artificial Intelligence, Papers and Concepts curated by Dr. Satya Malik.
Yeah, it is honestly a pretty incredible breakthrough we are looking at
Oh,
today.
totally. But before we really get into the weeds here, I should definitely mention to you listening that both of the hosts guiding this conversation today are AI generated.
Right, so just keep that in mind as we go.
Exactly. So today we are doing a deep dive into a paper from Microsoft Research. It's titled One-Bit AI Infra, Part 1.1, Fast and Lossless BitNet B1.58 Inference on CPUs.
It's quite a mouthful of a title, I know.
It really is. But the core mission of this deep dive is to explore exactly how this new BitNet.cpp framework allows massive large language models to run locally on standard everyday CPUs.
And why you should actually care about this is it's pretty simple. Right now, doing high-performance inference means you are completely bottlenecked by VRAM.
Oh yeah, you need those huge, expensive GPUs.
Exactly. Deploying a highly capable model basically forces you to provision these massive, power-hungry GPU clusters.
Which is incredibly expensive.
Exactly. And this tech basically just bypasses that silicon requirement entirely. It is paving the way for hyper-efficient, totally private, on-device AI.
So if you're a developer dealing with crazy cloud compute costs or just an enthusiast, this breakthrough turns your regular personal computer into a serious inference engine.
It really shifts the whole paradigm.
Okay, so real quick before we get into exactly how they pulled off this 1.58-bit math, this podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
All right, so getting into the actual paper, the very first figure has a data point that is just jaw-dropping when you think about hardware constraints.
Oh, the 100 billion parameter one, right?
Yeah. The researchers successfully ran a 100 billion parameter BitNet B1.58 model on a single Apple M2 Ultra CPU.
Just a single CPU. I mean, we really have to contextualize that for a second, because normally a 100 billion parameter model in FT16 would require something north of 200 gigabytes of memory just to load the weights.
You'd be looking at a multi-GPU setup just to get it off the ground.
Exactly. Getting it to run on a single workstation CPU is a massive shift.
It completely redefines the hardware floor for large-scale deployment. I mean, yes, the Apple M2 Ultra has a unified memory architecture, which definitely helps, but we're still talking about a consumer-grade chip handling a colossal workload.
And it didn't just load the model.
Right. It achieved an inference speed of 6.58 tokens per second.
Which puts it right in the sweet spot for practical use.
Yeah.
The paper actually notes that standard human reading speed clocks in at about 5 to 7 tokens per second.
So it perfectly matches how fast we actually read.
So what here is huge. You are generating text locally, entirely offline, exactly at the speed you can physically consume it.
That parity with human reading speed means the latency bottleneck effectively vanishes from the user experience. You don't have the network latency of an API call.
Right, no round-trip delays.
And you aren't waiting for a cloud cluster to batch your request with thousands of others. You ask a complex question, and your local machine just streams the output as fast as your eyes track across the screen.
Okay, let's unpack this. Because they compared BitNet.cpp to the current gold standard for local deployment, which is llama.cpp.
And the performance metrics are extensive. They took a highly systematic approach, testing across 12 different model scales.
Starting from 125 million parameters all the way up to that 100 billion architecture.
Exactly. And they evaluated this on two distinct architectural paradigms. ARM, using that Apple M2 Ultra, and by 86, using an Intel Core i7-17700H processor.
So we get a clear picture of both unified memory systems and traditional split memory desktop setups. And the speed upgrades are massive.
Very massive.
Looking at ARM architectures, the speedups range from 1.37x on the smaller models, scaling all the way up to a 5.07x speedup on the larger models.
And if you look at the x86 architectures, that Intel chip, the jump is even steeper. It reaches between 2.37x and 6.17x faster than llama.cpp.
Wow.
The scaling behavior is particularly interesting there. The larger the model gets, the more aggressively BitNet.cpp outperforms the baseline.
We definitely need to talk about the energy consumption data too, because running sustained inference on a CPU usually means thermal throttling and battery drain.
Right. The energy efficiency metrics track almost perfectly with the speed gains. They measure this in joules per token.
And looking at a 70B model on the Apple M2, The baseline llama.cpp consumed 28.02 joules per token.
And BitNet.cpp dropped that down to just 8.42 joules per token.
That is a 70% reduction in energy overhead for the exact same output. And on the Intel chip, for the smaller models, the energy savings hit 82.2%.
It is staggering.
It really is. It's honestly like swapping out a massive gas-guzzling cargo truck for a hyper-efficient electric scooter that somehow manages to carry the exact same payload.
That is a brilliant analogy. It completely changes the thermal and power constraints of deployment. When you reduce energy consumption by up to 80%, you open the door to running large-scale inference on edge computing nodes or mobile architectures.
Environments with strict power envelopes.
Exactly. So let's dig into how they are actually achieving this. What is happening under the hood?
The main problem has always been the weights. Traditional models use heavy, full precision weights, right?
Right, your standard FP16 or FP32 formats. The CPU spends so much time and energy just moving those heavy weights from RAM into the processor's registers.
The computation itself is almost secondary to the data transit costs.
Precisely. But the BitNet architecture fixes this by using ternary weights. Instead of full precision, the weights are constrained to just 3 possible states: -1, 0, and +1.
Which mathematically translates to 1.58 bits.
Because log base 2 of 3 is roughly 1.58, yeah. By using ternary states, you no longer need to execute complex matrix multiplications.
The heavy floating point operations GPUs are designed for.
Right. When you multiply an activation by -1, 0, or 1, it simplifies the entire operation into basic addition and subtraction.
And to maximize that simplified math on standard CPUs, BitNet.cpp uses 3 specialized optimized kernels. Let's look at the first one, the I2S kernel.
So I2S handles packing the weights into a 2-bit format offline and then unpacking them dynamically during the computation phase.
It reduces the memory footprint at rest?
Exactly, to conserve RAM and bandwidth. Then, as the weights hit the CPU, they are unpacked into int8 or int16 so the processor can execute standard operations. I2S is highly recommended when you have plenty of CPU threads available.
It keeps the cores saturated.
Exactly.
Then they introduce the TL1 kernel, which takes a different approach entirely. It packs 2 ternary weights into a 4-bit index.
But rather than doing the arithmetic on the fly, it relies on a lookup table, a LUT, with pre-computed values.
Because if you pack 2 ternary weights together, mathematically you have 3 squared, or 9 possible combinations.
Right, so instead of the CPU calculating the result every time, the TL1 kernel just uses that 4-bit index to point to a table that already holds the answers for all 9 states.
It basically skips the heavy math. The CPU isn't doing math, it's just retrieving a pre-calculated answer from a tiny table.
And that table sits right in the ultra-fast L1 cache of the CPU. The TL1 kernel is perfect for thread-limited environments, like when your machine is multitasking.
Makes total sense. And then there is the TL2 kernel, the ultimate compressor.
Yeah, TL2 pushes that compression even further. It squeezes 3 weights into a single 5-bit index.
Which is a 1-bit sign and a 4-bit index, right?
Yep. With 3 ternary weights, you have 27 possible states.
Huh.
By packing the data this densely, it reduces the overall model footprint by an additional 1/6 compared to the TL1 kernel.
That's a huge reduction.
It really is. The primary use case for TL2 is hardware facing severe memory or bandwidth limitations. It drastically lowers the amount of bandwidth required to feed the processor.
Here's where it gets really interesting. Because you would naturally think that cutting all these corners, using 1.58 bits and lookup tables, would totally destroy the AI's intelligence.
That is the standard trade-off, yeah. Usually when you forcefully truncate weights down to sub-4-bit levels, the rounding errors compound.
The network loses its granular nuances. You see hallucinations, repetitive loops.
A general collapse in reasoning capabilities.
But to prove that BitNet.cpp avoids this degradation, the researchers set up a wildly rigorous accuracy test.
They really did. They didn't just use generic benchmarks. They took a 700 million parameter model and ran it against 1,000 random diverse prompts from the Wildchat dataset.
And they evaluated the output token by token against a heavy, full-precision FP32 kernel.
The criteria were absolute. An inference sample was only considered lossless if it was an exact one-to-one token-by-token match with the uncompressed model.
If a single token diverged across the entire sequence, it was marked as a failure.
Exactly.
And under those punishingly strict conditions, the BitNet.cpp kernels-2S, TL1, and TL2 achieved exactly 100% lossless inference.
0 loss in accuracy.
Okay.
Every single token aligned perfectly with the full precision baseline.
Which is incredible when you compare it to the baseline. Specific kernels in llama.cpp, like TQ10 and TQ20, only managed a 1.4% exact match rate under those same strict conditions.
A 1.4% match versus 100%. It essentially proves that the 1.58-bit architecture isn't just a compression trick, it's a mathematically precise implementation.
You get the speed, you get the dramatic reduction in energy in VRAM, and you retain the exact operational intelligence of the model.
Because the BitNet models are natively trained or distilled to operate within these ternary constraints, the inference framework is executing the model exactly as intended.
It forces us to completely reconsider the trajectory of deployment. The barrier to high-performance inference has fundamentally shifted from the data center to local hardware.
It really leaves you with a provocative thought. If a standard desktop CPU can already handle a 100 billion parameter model losslessly using 1-bit architecture, what happens when this level of extreme quantization makes its way to our smartphones, smartwatches, or even home appliances?
It's a crazy thing to visualize.
Are we looking at a near future where the cloud is basically obsolete and every single device you own is natively a supercomputer?
That is a phenomenal question to end on. Thank you so much to you listening for joining us on this deep dive into Microsoft's 1-bit AI infrastructure. We really hope you learned something new about where the local deployment ecosystem is heading. If you enjoyed this, please subscribe to the show for more explorations into the cutting edge of AI. We will see you next time.